Oh, sorry, let me. Okay, CD-ROM. Check. Okay, can you see the website? Nampak ke? Okay, right, nampak. Right, good. So when discussing about collection probability, you can also come to this website to read the elaborated version. Okay, this is for solar cell mainly. So, but the basics of the PN junction collection probability are the same with what we've learned before. It's just that the contents are more tailored to solar cells, right? So we've covered most of the items that is discussed on this page. Okay, for example, if you can come here, you can see this collection probability. Let me just go through the sentences and recap what we've learned in the illuminated PN junction. So collection probability describes probability that a carrier generated by light absorption in a certain region of the device will be collected by the PN junction. Okay, we have discussed about the carrier generation in the depletion region, carrier generation in the quasi-neutral regions, and then the collections of carriers in the depletion region and both quasi-neutral region as well. So the carriers will be collected and then contribute to light generated current JL we discussed yesterday. But probability depends on the distance that the light generated carrier must travel compared to its diffusion length. Okay, so we discussed before that in order for the carriers to be collected, the distance that a carrier has to travel has to be less than its diffusion length. That means if the diffusion length is larger in comparison to the distance it has to travel, it will reach the destination. Okay, so the destination here means it will get collected. Or on the other hand, if the diffusion length of the carrier, either for electron or for hole, is less than the distance that it has to travel, so that means if it has to travel so long in order to be collected, but the diffusion length is only so short, the carrier will not be collected. Okay, it will recombine before it gets collected. So this is where it's important for you to go back to the definition of the diffusion length, right? Where it defines the distance traveled by a carrier from the point of generation until the point of recombination. So if the diffusion length is longer than the distance it has to travel, that means it can survive the journey, right? Survive the journey and get collected by the junction and eventually by the contact. Collection probability also depends on the surface properties of the device. We've discussed this one while discussing about recombination. We discussed about surface recombination. We discussed about bulk recombination. We discussed about surface recombination velocity and all the stuff. Collection probability of carriers generated in the depletion region is unity. We discussed this one yesterday, where we assume that the collection probability of the carriers generated in the depletion region is unity, because after all, depletion region or the PN junction itself is the one that functions to separate both carriers to opposite directions. Okay, so it's unity because electron hole pair are quickly swept by the electric field at the junction, right? Remember we discussed about the presence of electric field at the junction. It is the strongest in the junction region because we have the presence of surface charge on both sides. Where if you go away Whereas if you go away from your depletion region into the quasi-neutral region on the P side, quasi-neutral region on the N side, the electric field drops, right? Accordingly, because of the lack of the space charge region, right? Because we don't have a space charge region in the quasi-neutral region, right? Away from the junction, the collection probability drops. We discussed yesterday about this exponential decay. If the carrier is generated more than a diffusion length away from the junction, then the collection probability of this carrier will be low. Okay, so that means if you want the carriers to be collected for sure, we need to make sure that the carriers are generated within a diffusion length away from the PN junction region. So is this possible to control? What do you think? Is it possible to control the carriers to be generated only a diffusion length away from the depletion region? Is it possible? What do you think? Bolehkah kalau kita ada wafer, kata if you have a wafer here, say, so the wafer thickness is about 200 micron, for example, and the PN junction is right on the top of the wafer, say the top 200, 300 nanometers. So can we just make sure that the carriers are generated one diffusion length away from the depletion region and not in the rest of the areas in the wafer? Is it possible? Boleh tak? Yes, how about boleh tak tu, by boleh tak tu I mean can we not generate the carriers outside the one diffusion length away? Is it possible? What do you think? Possible? Maksudnya kita tak generate carriers dekat other areas. How do we do that? Okay, you say it's possible, Amirul and Haziq. How do you think we can do that in the real life? What do you think? Haziq and Amirul, will you unmute? What do you think? Just share your opinion. It's okay. Then we discuss. Okay, Haziq, what's up? So what do you think? Amirul, what do you think? Yes, you said yes. How is it possible? How to do that? How do you think you can do that? Will you unmute?
Because when we bring the PN junction closer to the surface.
Okay, so kalau you fabricate the PN junction, so how do you make sure that the carriers are only generated near to the depletion region and not away from the depletion region? Katalah ni you punya wafer, katalah PN junction is at the very top surface, 200, 300 nanometers. So how do you make sure that the carriers are generated within one diffusion length? Maksudnya, the distance within one diffusion length here means the distance between your depletion region to the point of carrier being generated is about LE or LH, not more than that. Boleh ke? How do you think, Amirul? So when you have the junction, so how do you then make sure that they are only within LE or LH from the depletion region in order to make sure they are collected? Haziq, what do you think? Boleh ke? For others, what do you think? Is it possible or impossible? Okay, kenapa you pening, Haziq? Let me know. Pening sebab apa you tak faham apa tu? Let me know. I will clarify again. Just unmute yourself. It's okay. Just ask question. It's fine. Kat mana you pening? Okay, go.
The question, Doctor.
Oh, the question.
The question.
Okay, you are the wafer. So this is your wafer.
Okay.
Oh, the question lah, right? Okay, you are the wafer. So the wafer is 200 micron thick, for example. Okay. So your PN junction, normally we fabricate your junction on the surface, right? So say it's about 200 to 300 nanometer thickness on the top surface out of the whole 200 micron. And the PN junction thickness is very, very thin, right? So, is it okay so far?
Yes.
Okay. So we discussed yesterday that carriers generated near to the depletion region will be collected, right? So
Oh,
the probability of collection will be unity in the depletion region. But if you want to have the carrier to be collected, at least the distance of the carrier away from the depletion region has to be one diffusion length away to still make sure they get collected walaupun dia bukan dalam depletion region. Maksudnya, if they are away from the depletion region by LE or LH, they will still get collected because they can travel, right? They can travel by that distance, exactly, right?
yes.
So they can travel by that distance, and that is the journey they have to travel after all to get to the depletion region in order to be collected. Faham?
Dekat tu faham.
Okay, so my question is, so kita ada 200 micron. Kata you punya the diffusion length is very small, for example, like 2 micron or 3 micron only from the depletion region. And your wafer thickness is like 200 micron. Boleh tak? Is it possible we only control our carrier generation within LE or LH from the depletion region only and nothing outside the depletion region? Maksudnya
So,
there's no other regions ya dalam silicon ni kat belakang ke, for example, that
oh,
actually generate the carriers yang tak akan sampai pun kat PN junction tu sebab it's just too far away, isn't it? So it's like
okay.
200 micron at the back, and yet they have to travel like 200 microns in order to get to the depletion region to be collected. But the diffusion length is probably like 3 micron. Maksudnya dia tak akan survive lah. It won't get to the PN junction, right? Because they are just too far away from the PN junction to begin with.
I see.
So boleh ke kita nak make sure tak ada carrier generated outside the LE or LH punya range?
Nak make, boleh ke kita nak make sure tak ada langsung generation?
Yeah, is it possible? Is it possible at all?
Uh, oh, tapi kalau based on graph saja macam
Yes.
graph yang tengah tunjuk sekarang ni,
Okay.
I don't think that it can be further narrow it down.
Okay. Okay.
So I think no.
So maksudnya it's not possible, right?
Yes.
So the moment you have the volume of your material, you will have carriers. The moment you have this volume of material interacting with light, you will have electron hole pairs generated everywhere, isn't it? As long as the flux of the incident light strikes through the material, isn't it? Remember the gx punya function yesterday? Well, the function exponentially decays. Cumanya, even though it decays at the back into the depth of the silicon, vertically here in this case, you still gonna get some flux at the back, isn't it? Unless flux sudah habis ya sampai ke belakang, right? So the moment you have light interacting with your material, and provided if the photon energy is more than or equal to the band gap, you're gonna get electron pair generated, isn't it? Betul. Then it's only a matter of whether the generated carriers can get collected or not. You may generate the carriers throughout the volume of the wafer, but you may or may not collect them because some of the carriers are just too far away from the junction, isn't it? So what I'm trying to say here is it's not, well, by default, it's not possible to control the generation of the carriers to restrict the generation of the carriers to only one diffusion length away from the junction, LE or LH away. It's not possible, but if you think about it properly, it could be possible as well. How is it possible? Well, by default, it's not possible if you're talking about the wafer, but if you're talking about a thin film, for example, so instead of having 200 micron of this wafer, you might only need, for your technology, for your solar, for example, katalah solar cell, light absorbing device, you may only use a 2 micron or 3 micron of your device thickness, which happens to be within the depletion region of the carriers, right? Means you don't change the diffusion length of the carriers, but you change the device thickness, isn't it? So when you change the device thickness, so that means now the whole wafer thickness is only about 3 micron thick, and your diffusion length is probably about 3 micron long. Maksudnya carrier generated at the back of the device, which is 3 micron thick, is still within the diffusion length away from the PN junction, right? So in that case, for the thin film technology, then it's easier to collect the carriers even though they are far away from the junction. Well, they're not far away though, because the whole device thickness is only like 2 to 3 micron to begin with. So now you don't manipulate the diffusion length, but you manipulate the device thickness. It can be done. So when we talk about the thick wafer, of course, it's very, very hard unless you manipulate the diffusion length of the carriers. So this means, what I'm trying to say here, my point is, when you talk about collection probability, when you work on a thick wafer or a thick device, you need to make sure that your diffusion length is very, very long, because you cannot play with the device thickness already because it's very thick to begin with. Then you really have to work on the diffusion length of the carriers in the device. On the other hand, if you work on thin devices, you don't have to worry so much on the diffusion length of the carriers because the device thickness is already thick, but it's already thin to begin with. Just like two cases, kalau if you're riding a motorbike, for example, motorcycle, your tank is very small, and you are traveling only like 10 kilometers across. Katalah merentas daerah dengan kebenaran polis. So you're crossing like 10 kilometers away. So with such a small tank, you can make it, right? Because the distance is only like 10 km away to begin with. So on the other hand, if you have a small tank, the very same tank, small tank, but you have to travel like 500 kilometers to get from Perlis to Melaka, for example, Mirul nak pergi Melaka, for example, then it's like, I don't know, perhaps Johor. Then you use the very same tank, but you want to travel long. Of course, you won't be able to get to Melaka with the same tank size. What you have to do is you have to refuel, right? You have to manipulate your diffusion line in order to get to your destination. So that's the whole point. So when we talk about devices later on, we're gonna look at some devices which are thick in nature, and we're gonna also look into some devices which are thin in nature. So nanti kita akan tengok, some will be presenting about JFET, MOSFET, MOSFET ada BJT, organic solar cell, cadmium telluride, photodetectors, laser diodes, LEDs and stuff. So you have to relate these to your device nature, right? The diffusion length, the device thickness, the junction properties. You should be able to relate, okay? So that's my point out of this whole one sentence. So similarly, if the carrier is generated closer to a region with such a surface with higher recombination than the junction, the carrier will recombine. The impact of passivation and diffusion length is illustrated below. Okay, so this collection probability graph down here is close to what we discussed yesterday, but it's more on the solar cell. If you talk about the application, so for this particular graph, So this green, this yellow region in the middle is the PN junction. It is the depletion region. And we discussed about the unity carrier collection in the depletion region. And then the collection probability falls off exponentially as the carriers are generated away from the depletion region. Okay, so you can also see that we have two surfaces, the left hand side and on the right hand side. Left hand side is probably the front side, and the rear surface on the right hand side is at the back side. Okay, so to relate this to the device properties to some extent, we discussed about the passivation, right? Still remember the passivation in order to suppress recombination last time we discussed? So you can look at these few cases to relate back to the passivation. Lupa dah. So remember the passivation is a process that we use to suppress recombination. We discussed this during recombination topic. Remember about the surface recombination velocity, SRV? Right? When you want to have a low surface recombination velocity in order to avoid the carriers from rushing to the surface to recombine. Okay, we want to have a low SRV instead of high SRV. Okay, low SRV means low recombination, low surface recombination. High SRV means high surface recombination. The unit is centimeter per second. Okay, so the passivation is a process. Let's recall the passivation is the process that we use in order to suppress recombination. Okay, so if you look at these two surfaces on the left and on the right, okay, kita akan tengok animation kat bawah later on, but let me just go through this first. So if you look at the surface on the right, okay, look at the rear surface on the right. I'm pointing to the right now. So if your device, solar cell or whatever, this is for solar cell, but it works for other devices as well. So if you look at this rear surface on the right, if you have a very good surface, well passivated, that means your surface has the surface passivation, is already surface passivated. So your collection probability will take the green profile, this green one. Okay, so if you look at the real surface on the right hand side, ni dekat secondary y-axis, look at this collection probability right on the y-axis. So if you look at the scale, so that's probably about 0.5 or 0.4 plus, right? On the secondary y-axis, on the surface. So that means quite a number of carriers will still be collected if it's generated away from the surface because the surface is well passivated to begin with. On the other hand, is the surface, if the surface is not passivated or it has a poor passivation quality, that means you passivate but you don't passivate well, ataupun you don't passivate at all. So the collection probability will take this red profile. So that means right on the surface, the secondary y-axis, the collection probability right on the surface is 0. But if you go into the device, it's going to get higher and higher and higher gradually, right? But it's way poorer if you compare to the green curve, right? And the third case, if we look at the blue curve, this blue curve, you can look at the decay falls off to 0, not even half of the distance between the rear surface to the depletion region. So maksudnya kat sini, the collection probability is already 0 halfway through the thickness between the depletion region and your rear surface. So for sure, if you look at this blue curve, if your carrier is collected, if generated here, so I'm pointing here on the axis, kalau you generate your carriers here, it will not be collected for sure because the collection probability at this particular point, I'm pointing on the cursor now, using the cursor now, is 0. So no way it's going to be collected at all by the junction. Okay, so the same thing also applies on the left hand side of the PN junction. Okay, sama ya. So you can come down here later on. Okay, let's just go through this animation for you to understand more on the previous concept that we've learned. Let me just reduce the size a little bit so that you can see the impact. Okay, so okay, this is your PN junction, and say your left hand side, your green red curve is on the front side of the device, which is situated on the left hand side, and the right hand side of the graph is the right hand side, is the back of the cell. Okay, kalau at the back of the PN junction lah. So let's look at the effect if you vary the emitter diffusion length. Emitter is the region with the red graph here. Emitter to the junction is labeled here on the left, and on the right, base distance to the junction. Base is the whole thing here to the junction. Remember, the emitter and the base here is used for solar cell. Okay, so kita pakai emitter and base, but you're going to see later on when you do the presentation, some other devices also use the concept of emitter and the base and everything. So the other day, we own specific terminology to specific devices. But since this website is for solar cell, so the terminology is emitter and base. Okay, emitter is the very thin. If you're talking about the PN junction, emitter is the very thin layer on the surface. Say your wafer is P-type, your emitter will be the thin N-type, 200 nanometer or so, lebih kurang. And the whole base, the whole volume will be the base. Okay. So what if you play with the emitter diffusion length? Let's look at this. So now if you look at the graph on the left hand side, the dimension on the x-axis, emitter to the junction is about 1 micron, right? Negative 1 micron to the left to 0, so that's about 1 micron thick, more or less. So if you play this animation, so kalau kita reduce the emitter diffusion length, let's look at the collection probability. So it's going to go down, 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 sampai 0, just like what we saw here, okay, on the top graph. So the top one is the good one, the low one is the bad one. So this one is the bad one, if you like. And if you improve the quality of your emitter, your collection probability increases accordingly, right? So that is the effect of emitter diffusion length. So let's look at the emitter surface recombination velocity, SRV. This is emitter SRV. You can look at the unit there, centimeter per second. So if you increase your SRV, what do you think will happen to the red curve? Will it increase or decrease? I can see your mouth, but I couldn't hear you. Increase or decrease? If you increase SRV, the red curve will decrease or increase? Increase or you said increase? Azik say increase? Decrease or increase? Camilo said decrease. Okay, kita nak higher. Do we want high SRV or low SRV in our device to be a good device?
Low SRV.
Low SRV, right? So let's look at this now. If you increase your SRV, look at your emitter diffusion length. Decrease, right? So this means when you increase your SRV to say to infinite, so in this case 1 to the 6 centimeter per second, so your emitter collection probability will reduce drastically. So if you talk about the high SRV here, in this case, we are talking about poor passivated surface. If the surface is poorly passivated or there is no passivation at all, you're going to end up with high SRV on the surface. Just like this blue curve on the left and on the right. On the other hand, if you improve the passivation quality, or you do a proper passivation on the emitter, let's look at the SRV. When you decrease the SRV, and as a result, the emitter collection probability increases accordingly up to some point, which is limited by the emitter diffusion length up here. Okay, it's interrelated somehow. Okay, so now let's look at the base, the blue curve on the right. Okay, so what if we increase the base diffusion length? So if your carrier diffusion length in the base increases, the collection probability on the right will be increased as well. Okay, just like what we understood before. Okay, and the same goes to the base surface recombination velocity as well, the SRV. If you increase the SRV of the base, the collection probability reduces accordingly. If you passivate the surface well, the real surface well, the blue punya side, the real cell tu, cell real tu yang label tu, then you improve the collection probability accordingly. Okay, So this is the effect of the emitter diffusion length, base diffusion length, SRV in the emitter, SRV in the base, okay, that we learned before. So the rest are exactly the same that we learned yesterday. The JL will be given by this integral, and then collection probability away from the junction, generation rate, the GX factor. Okay, you can also play with the light absorption, the wavelength into the device, for example. Okay, so remember last time we talked about, when we talk about generation last time, we talk about blue photons will be absorbed at the surface, right? Green photons will be absorbed in the middle, let's say, and then red photons will be absorbed at the back, isn't it? So yang mana short wavelength will be absorbed on the front side, middle wavelength will be absorbed on the rear, in the back, in the middle, and then the long wavelength will be absorbed at the back, right? So you need a very thick volume of material in order to absorb the long wavelength. So you can also see this effect here. So this is the spectrum that I'm playing here is the wavelength of the light. So now it's about 290 nanometer. So now look at the normalized generation rate. So as you increase the wavelength, the generation rate goes into the device, into the depth. Okay, you are getting more and more generation into the volume of the device. Okay, so remember what is the bandgap of silicon? So what is the bandgap of silicon, and what is the corresponding wavelength of that bandgap? Anyone? Bandgap of silicon and the corresponding wavelength of the bandgap. 1 times 10. Bukan. The bandgap is it? Bandgap of silicon.
1.12. 1.12.
1.12, right? 1.12, okay? 1.12 EV. And then what is the corresponding wavelength of that bandgap? If you convert the energy into wavelength. Berapa? What do you get? What is the equation that you need to use? 1240 divided by 112, right? 1.24. The equation, remember the conversion 1240 divided by 1.12. Dapat berapa? Cuba divide 1240 divided by 1.12. Anyone? 1240 divided by 1.12 EV. What do you get? That will be the corresponding wavelength, right? 1100, right? So that is the 1100 nanometer. So let's play with this cursor. So let's try to see how much thickness is required in order to absorb up to 1100 nanometer in silicon. So you can increase this wavelength. Now it's 895. Increase further up to 1100. Huh? Wow, you can see now it's the scale on the x-axis is only 100 micron, right? And the profile is now beyond 100 microns. So that means you need a very thick silicon in order to completely absorb the wavelength. So now I'm going up to 1100. Oh, tak sampai ini. You can play with this later. Okay, 1100, I stop there. Look at the thickness required of the silicon, crystalline silicon thickness required in order to absorb 1100 nanometer, up to 1100. Sebelum ni kita belajar, we discussed before that in order to absorb the light, high energy photons, blue photon will be absorbed at the surface, green photons, medium energy will be absorbed in the middle of the surface, in the middle of the bulk, and red photons will be absorbed at the back. So, and this whole thickness has to be thick enough in order to absorb the whole wavelength. Now you see on this cursor, on this animation, in order for you to absorb up to 1100 nanometer of the photons, maksudnya daripada blue photon, green photon, yellow photons, up to red photons, from the UV up to the red photons, you need infinitely thick silicon, right? is way beyond 100 micron in order to completely absorb from UV to visible to IR up to 1100 nanometer. So that means if you use 200 micron of the crystalline silicon wafer, do you think you can absorb everything up to 1100 nanometer for crystalline silicon? What do you think? Yeah, I will leave this question for you to search. I want you to go back and try to search. In order for the crystalline silicon to absorb up to 1100 nanometer, how much thickness of the silicon is required? Is 200 micron enough? Or 300 micron? Or 400 micron? Or 500 micron? Or 600 micron? Or 1000 micron? Or beyond 1000 micron? Now you see on the graph that it's already out of the scale, right? So it goes beyond 100 micron here in order to absorb this 1100 nanometer, which is 1.12 EV photon. Okay, so go back and try to find out how much thickness of the silicon is required in order to completely absorb up to 1100, which is the age of the band gap. Kalau you jumpa, let's say, very thick, then how come the industry only uses 180 micron to produce solar panels and everything on the roof? How come? And how is it done? Katalah you jumpa 1000 micron, and then we only use like 180 micron in the industry. How come is it possible? So this is all the physics behind it, okay? So I leave it to you to search for that, okay? So I'll leave you on this page. So now I'm going to continue to the metal semiconductor junction. Now saya akan cover just a bit of it because it's already 10:40. So is it okay now for the collection probability? Can you see the concept that we've learned before on the animation, the correlation now? Is it okay? Right, good. So now let me go to the metal semiconductor junction. I will go for perhaps 10 minutes. Okay, can you see the slides? Okay, good. So this is about metal semiconductor junction. So if you can recall, from day one, we learned about the material, the semiconductor material, resistivity against conductivity, crystallinity of the material, and then the p-type, the n-type, the p-n junction, the physics behind the carrier transport phenomena, and then majority carrier concentration, minority carrier concentration, diffusion length, collection of the carriers as it get away from the junction. So now we are arriving at the end of the quasi-neutral regions, right? So if this is your p-n junction, for example, if this is your p-n junction, okay, this is your p-n material. So we have covered all the stuff inside here. We have covered all the stuff here. We have covered all the stuff here. And now we are at this interface. Okay, we are at that interface where you put on your metal in order to extract your carriers to the outer circuit. So we're going to be discussing about these interfaces now. Metal semiconductor junction. So as usual, challenge what you've learned. We've discussed this one a little bit. Well, go back to this and try to understand the gist of the previous topic. This is about the minority carrier generation upon illumination, where they get to be the majority carriers upon crossing the junction. And then you should be able to sketch the carrier, the probability of carrier collection that we discussed just now, away from the depletion region, away from the p-n junction. Okay, and then why the collection probability falls off with distance. Okay, and also can the probability of the carrier collection be equal to unity and p-n junction. Okay, so go back and try to recap on this. So now, why contacts? Any idea why do we have the contacts? why contacts? If you look at this is your silicon wafer, for example, and this is your silver contact on the front side. So at the back that we don't see now, at the back is an aluminum contact for this particular case. Okay, so why contact? Why do you need to have the contact? Okay, kenapa perlu ada contact? Anyone? Can you don't have any contact on the device? Can we not have any contact in order to run the device? Boleh ke tak ada contact? Can we go contactless? No, Amira said no. Kenapa no, Amira? So the one on the right here, this one is the contact as well. This is gold contact. Okay, gold like AU, all of them. Gold contact. So this one is the back contact like at the back, at the rear side of the device. Can you have can you not have any contacts at all on the device? Cannot. The answer is cannot. You cannot, because how are you going to withdraw your carriers? You're gonna need to have a medium of high conductivity in order to extract your carriers, right? Usually we talk about metals. And that's why we discuss about metals, insulators, semiconductors with varying conductivity against resistivity, right? We discussed in our very first class. Okay, so you need to have contact in order to extract the carriers to the outer circuit. So now imagine if you are an electron. So imagine yourself as an electron. So this is how you're going to see the contact. So doors to the outside world. The contacts are the doors to the outside world. So this is how carriers, electron and hole in semiconductor, see metal contact. So just like the way we are in the MCO now, we are in the house, we are the electrons in the device, and the doors need to be closed all the time. Or you can just go up to your yard, for example. Tak boleh keluar jauh-jauh sangat kan, sebab MCO and everything. If you can recall last time during MCO 1.0, we are completely locked down, right? So we can't go out much. But tak macam sekarang. Sekarang is a bit relaxed in that case. Even though it's more strict than the MCO2, tapi you are trapped inside. Okay, just imagine if you're an electron and you are trapped inside the device, you cannot go out. So you cannot contribute anything to the device. Okay. So if you're an electron, you want to go out of the device to contribute to the device operation. Okay. So if you need to be extracted, then this is how you're going to see the metal contacts. So it's the way out of the device. So if you don't have the metal contacts, you're going to be in the device forever. Okay, literally forever. Okay. So previous chapters we've covered about semiconductor material in the same is the same throughout the structure. We call that as homojunction, when the PN is of the same material and the same band gap as well, same crystallinity as well, if you like. So we call that homojunction. And now we're going to look into metal semiconductor junction, and also after this we're going to cover semiconductor heterojunction. What if you put zinc oxide on silicon? What if you put cadmium sulfide on cadmium telluride? What if you put silicon gallium arsenide? Or you can go indefinitely, right? Various materials on some other different materials. So semiconductor heterojunction. So they still form PN junction, but they are of a hetero in nature. They are not the same material. They are not with the same band gap. They are not with the same crystallinity properties, perhaps. So metal semiconductor junction and semiconductor heterojunction can also produce diodes, PN junction. So semiconductor devices or integrated circuit must make contact with the outside world in order for us to extract the carriers, or in fact, for us to inject carriers into the device. So it's not only about collecting the device or extracting the carriers outside. You might also want to inject carriers through the metal contacts. Okay. Remember, if you talk about the LED operation, if you like, LED is the opposite of solar cell, right? So in the solar cell, you shine the light, then you harvest electricity, right? On the other hand, for LED, you need to inject the current in order to produce the light. So in this case, you need to inject the current through the metal contacts into the device in order to induce radiative recombination in order for you to have the LED. Okay, so in this case, you still have to go through the contacts in order to realize the device operation. Okay. So when you talk about contacts, there are two types of contacts. So let me just go briefly. So it's already close to 10:50. So we have Schottky contact and we also have ohmic contact. Schottky contact is called a rectifying contact, where it only allows the current to flow in one direction, just like our PN junction. Remember, we talk about rectifying properties. So it only allows the current to flow in one direction. So it has high resistance in nature. On the other hand, you have another contact which is called ohmic contact or non-rectifying contact. So it looks like that. So the resistance is low, and then it allows the current to flow in both directions. Okay. So when you talk about rectifying, it's only one direction. When you talk about non-rectifying, it allows the current to flow in two directions, in both directions. So Fermi energy represents chemical potential of electrons. Remember last time when we talked about Fermi energy, we talked about this definition as well. It is a chemical potential of electrons. Okay. Whenever we have two materials in contact to form the junction, equilibrium is established or is achieved, and the Fermi level is the same throughout the device. Okay, remember we talked about the alignment of the EF throughout the device. The moment you have the thermal equilibrium condition, P and N, we have a single Fermi level or single chemical potential throughout the device. So in order for us to determine either we're going to have ohmic contact or Schottky contact, it is dependent on the work function of both materials. Work function, the phi, okay? The phi, the work function of the metal, work function of the semiconductor material. So this will determine whether you're going to end up with ohmic contact and the Schottky contact. And it also depends on whether the semiconductor is of N-type or of P-type, okay? If you have a metal which has a work function, before that, let's recall what is the work function. What is work function, by the way? Dah belajar kan dulu kan? Dah belajar in quantum mechanics ke or modern physics? What is work function? Anyone? A brief definition. Apa benda work function ni? Did you learn about photoelectric effect last time? Okay, Shreya said minimum energy for photoelectric effect. Okay, what is photoelectric effect then? Kenapa you kena ada minimum energy? What do you need why do you need the minimum energy in order to do what? To be more specific. Ada belajar kan photoelectric effect dalam modern physics ah? Is it? Modern physics was it? Or quantum mechanics ke? Or classical versus modern quantum physics? Minimum energy required for electron to be ejected from the surface, right? Minimum energy required to excite an electron off the surface. Light on metal producing electrons. Yes, all good. Okay, so the minimum energy required to remove electron from the surface, if you like, or from its valence band in order to be free or in order to be excited, if you like. Right? So that is the work function of the device. So in order for us to know whether we're going to end up with ohmic contact or metal or Schottky contact, if, for example, case number 1, if your work function of the metal is higher than the semiconductor, and you're going to use that contact on N-type silicon, for example, then you're going to end up with a rectifying contact. Okay. On the other hand, if you use the very same metal, which has a work function higher than the silicon, or semiconductor in this case, generally, but on p-type silicon, you're going to end up with ohmic contact. Okay, so maksudnya if you use for you end up with rectifying contact, you're going to have that kind of nature. If you end up with ohmic contact, you're going to end up with this kind of nature, the IV curve. And the same is opposite if you have a work function of the metal smaller than the silicon or the semiconductor on n-type, on p-type. So on n-type, you're going to end up with ohmic, and on p-type, you're going to end up with rectifying contact. So it's going to be opposite. So we're going to look at it later on. Why is it so? And we just finished with one page, the last one. So when you plot later on the metal semiconductor, we're going to work on the band diagram as well, just like what we did on PN junction and the Fermi level and everything last time. You're going to be drawing the band diagram of the metal semiconductor interface as well. So we're going to use the vacuum level E0 as our reference, the top level, right? Energy of the free electrons. The difference between vacuum level and the Fermi level, we're going to draw later on in the next class. The difference, the distance, the gap between the vacuum level E0 with the Fermi level is called work function, or the energy, the minimum energy required to remove the valence electron to be free, to be excited of the material. Work function is an invariant property of material, is the minimum energy required to free out electrons from the metal, just like what we saw in photoelectric effect, right? So we have a selection of metal contacts in order to be that can be used on our semiconductor materials with different work functions. For example, if you talk about silver, we're talking about 4.26 eV, palladium 551, tungsten 4.55. You can in fact map this on a chart of a spectrum from a low work function up to high work function with a range of different metal contacts. And on the other hand, we also need to know the electron affinity of the semiconductor material that we're going to use, so that we can do some calculations related to it. Silicon in this case has 4.12, gallium arsenide 4.07, and you can also refer to the rest. So in our class tomorrow, we're going to see how does a Schottky contact look like, and then what are the calculations related to the Schottky contact, and then what are the physics behind the Schottky contact, and also on the ohmic contact. Okay. So I'm just gonna stop here. 10:55 already. So is it okay so far with the introduction to the metal semiconductor contacts? Okay. Maybe one question I would like to ask you before I finish off. Does the contact have to be a metal? Does it have to be a metal all the time? If you have an idea, can we not use metal as a contact? Anyone?
Yes.
Okay, yes. Why is that so?
As
Okay,
long
apa tu? So,
as long as
as long as
it has good conductivity.
okay, if not metal, then what are they? So you said high conductivity, right? And we learned about the spectrum of conductivity versus resistivity in the very first class, isn't it? Metals, semiconductor in the middle, and then insulators. So these metals, high conductivity, low resistivity. So if it's not metal, then what else can be used? Has it said semi-metal? Yes, semi-metal can also be used. If it's not semi-metal, then what else? Maybe you've learned something before. With good conductivity. If they're not metals, they are not semi-metals, then what could they be? Any other answers, guys? Before we wrap up the class? Contacts do not always have to be metals, but generally they are metals. Kita lalu pakai copper, silver, aluminium, platinum, gabung metal, transition element can be used. Transition element, for example, Cornelia, do you have any examples? Gabung metal, alloy. Well, yeah, alloy can also be used. Yes, alloy. Okay, if it's not metal, then it could be alloy. It could be semi-metals. Ada lagi? So now you start thinking about other options than metals, right? Ada lagi? The very last option that we discussed in this course.
Glass.
In the apa?
Glass.
Amira?
Glass.
Glass? Is glass a conductor?
No.
Mercury? Okay, you try to check. Mercury can also be used as a metal, as a contact. Boleh kah? Hg, right? Ada orang pakai Hg as contact kah? Alia, you want to elaborate something on that? In our last minute of the class. Ada satu lagi kita nak belajar dalam this course. Alia, come on. Al is metal, right? Al, silver itu common lah. My question is, if it's not metals, then what else can be used as contacts? Semi-metals, alloy. Alia said mercury. I'm not sure. We have to check on that. Ada lagi satu lagi kita nak belajar dalam this course. Halfway through this course. Yeah, there you go. Degenerate semiconductors. What is the example, Shayes? The obvious one that we learn in this course.
ITO.
ITO, yeah. Indium tin oxide, or generally we call them as apa? TCO, transparent conductive oxide. Okay, they are not metals. They are semiconductors, but they are degenerate in nature. They are transparent. Metal shiny kan? Kalau you tengok metal, it's reflective, isn't it? But TCO, you cannot see the presence of TCO. They are transparent in nature. They are conductive in nature. The key word here is conductive, just like what Amiro said just now. So as long as you have conductive materials that are conductive enough, they can be used as contacts. But conventional materials, we use metals, but they don't have to be necessarily metals. Okay. So sekarang dah nampak kan? Metals, semi-metals, alloy, what else? TCOs, degenerate semiconductors. So when you talk about these TCOs, that means you can also use semiconductor as your contact, but they have to be degenerated semiconductors, not general, typical semiconductors. All right, then done. Let's continue with our metal semiconductor contacts tomorrow. Okay. Bye-bye. Thank you. Assalamualaikum. Stay safe.